Somewhere beneath the quiet farmland that straddles the border of France and Switzerland, there is a machine so vast, so audacious in its ambition, that describing it in ordinary language almost feels inadequate. A 27-kilometer ring of superconducting magnets, chilled colder than deep space, hurls the fundamental building blocks of matter around in circles at nearly the speed of light before smashing them together in the hope of glimpsing the conditions that existed a fraction of a second after the birth of the universe. We call it the Large Hadron Collider, and we built it to answer one of the oldest questions our species has ever asked: what are we, at the deepest possible level, actually made of? For decades, we believed we already had a very good answer. We believed we understood the rules of the game so thoroughly that the only work left was mopping up the details. But in recent years, something strange has started leaking out of the control rooms and data centers of CERN. Whispers, small, stubborn inconsistencies that refuse to behave the way our equations insist they should. It is as if we have spent our whole lives admiring a flawless mural, only to notice, almost by accident, a hairline crack running through the plaster. And when you lean in close and listen at that crack, you do not hear the comforting hum of the universe you already know. You hear something else, something that textbooks never prepared us for. We may be standing at the edge of a discovery that quietly rewrites everything we thought we understood about space, time, and the nature of reality itself. And in the pages ahead, I want to walk through that crack with you, one careful step at a time. Before we can appreciate why a few stray data points have physicists losing sleep, we need to understand exactly what it is we thought we already knew. Picture an exquisite antique pocket watch, the kind passed down through generations, heavy in the hand, ticking with an almost hypnotic precision. Pop open its brass casing and you find a small universe of gears, springs, and levers, each one doing exactly one job, each movement perfectly predictable. For the better part of a century, physicists have been doing something remarkably similar with the universe itself. We have been prying open the back panel of reality, looking past the wood of the chair beneath you, past the skin and bone of your own hand, down to the tiny mechanical parts that make existence tick. We call the result of that century of work the Standard Model of particle physics. And it is, by almost any measure, the most successful scientific theory ever constructed. It is part blueprint and part poem, a compact set of equations that describes, with staggering accuracy, everything you can see, touch, and measure. According to that blueprint, all matter boils down to a short list of fundamental ingredients. There are quarks, which huddle together to build the protons and neutrons at the heart of every atom. There are electrons orbiting those atomic cores and giving rise to chemistry, electricity, and ultimately to life. And there are neutrinos, ghostly and nearly weightless, streaming through your body by the trillions every second without leaving so much as a whisper of a trace. Holding these particles together and pushing them apart are four fundamental forces. Gravity, which keeps your feet on the ground. Electromagnetism, which powers every light bulb and every neuron in your brain. The strong force, which glues the nucleus of an atom together against its own violent urge to fly apart. And the weak force, which quietly drives the nuclear furnace burning at the center of the sun. Put it all together and you have an architecture of breathtaking elegance, tidy, symmetrical, and for a long time we assumed it was essentially finished. There was, however, one stubborn gap left in that blueprint. For decades, physicists could not explain why any of these particles have mass at all. The equations worked beautifully as long as everything was assumed to be weightless. But the moment you tried to explain why an electron weighs something and a photon weighs nothing, the whole elegant structure threatened to fall apart. The proposed solution was an invisible field stretching quietly through every point in space, a field that certain particles wade through as if pushing through molasses, gaining mass in the process. Finding proof of that field meant finding its associated particle, the long-sought Higgs Boson. And that search was one of the primary reasons the Large Hadron Collider was built in the first place. Finding a single particle hiding among trillions of collisions required an approach that sounds almost violent. Imagine trying to understand the inner workings of that antique pocket watch, not by gently unscrewing its casing, but by hurling two identical watches at one another at tremendous speed and then sifting through the wreckage of springs and gears that come flying out. That, in essence, is what happens inside the collider. beams of protons are accelerated to within a hair's breadth of the speed of light and smashed together, briefly recreating energy densities not seen since the earliest moments of the cosmos. In July of 2012, that extraordinary gamble paid off, and the Higgs boson was found. I remember the mood in the physics community that summer. It was pure, uncomplicated triumph. The last missing gear had apparently been located. The standard model had been vindicated in spectacular fashion. And for a brief moment, it genuinely felt like we might be closing the book on the fundamental structure of matter. Nature, though, has never been especially interested in giving scientists a tidy ending. As the collider kept running long after 2012, smashing particles together with ever greater energy and gathering colossal mountains of new data, the debris flying out of those collisions slowly started telling a different story than the one we expected. Certain measurements began drifting quietly but persistently away from the predictions of the standard model. Nothing dramatic, nothing that would make headline news on its own, but the kind of small, stubborn discrepancy that experienced scientists learn never to ignore. Think about flipping a coin. If it is perfectly balanced over 1 million flips, you expect something extremely close to a 50-50 split between heads and tails. But if that coin keeps landing on heads 60% of the time, no matter how many times you repeat the experiment, eventually you have to admit the obvious: the coin is rigged. Something hidden inside it, invisible to the eye, is quietly tilting the outcome. In certain corners of the Large Hadron Collider's data, physicists have effectively been flipping subatomic coins, and every so often the universe has come up heads a little more often than it should. To understand exactly where these particular coins were being flipped, it helps to meet a particle called the muon. Think of the muon as the electron's heavier, short-lived cousin, roughly 200 times more massive, but otherwise behaving in every measurable way exactly like an electron. Same electric charge, same interactions with light, same fundamental personality, just built on a larger scale, like a lead bowling ball compared to a small glass marble. According to the standard model, nature is supposed to be scrupulously fair between these two particles. A principle called lepton universality insists that the fundamental forces cannot play favorites between an electron and a muon. Yet in a series of experiments studying the decay of particles containing what physicists call beauty quarks, researchers noticed something that raised eyebrows across the field. When a beauty quark disintegrates, the rules demand that it should produce electrons and muons in equal proportion, a clean 50-50 split. For a while, the detectors seemed to be seeing something different, a persistent lean toward electrons over muons that showed up again and again as the data accumulated. At first, the natural assumption was a statistical fluke or a subtle flaw in the analysis. With billions of collisions to sift through, small illusions of significance appear all the time and typically dissolve once you gather more data. So physicists gathered more data, tightened their methods, and checked their own reasoning as rigorously as they could. And for a stretch of years, that anomaly stubbornly refused to go away, sitting there in the numbers like an unwelcome guest who would not take the hint to leave. Sit with what a result like that would actually mean if it held up. If nature genuinely treats muons differently than electrons in defiance of one of the bedrock assumptions of the standard model, then some hidden mechanism must be at work that our equations do not yet include. Something is quietly tilting the scales, and physicists have spent years chasing exactly what that something might be. One tantalizing possibility is an entirely new fundamental force, a fifth member to add alongside gravity, electromagnetism, and the strong and weak nuclear forces. One so faint and so specialized that it only reveals itself in the extreme violence of a particle collision and stays essentially invisible in ordinary daily life. Another possibility is not a new force at all, but a new particle. Something enormously massive that flickers into existence out of the quantum vacuum for an almost unimaginably brief instant, nudges the muon just slightly, and vanishes again before any detector can catch it directly. Theorists have given these hypothetical culprits names like leptoquarks or Z-prime bosons, though it is worth remembering that a name is often just a polite label for our own ignorance. What these anomalies really forced the field to confront was the possibility that the standard model, for all its genuine successes, might only be the visible surface of something much larger and stranger underneath, a shallow layer sitting atop a far deeper structure we have barely begun to map. And notably, this is also where honest science shows its own integrity as the LHCb collaboration continued refining its measurements in the years that followed. Much of this particular anomaly in beauty quark decays gradually faded, with newer, more precise results turning out to be more consistent with the standard model after all. That outcome is not a disappointment so much as a demonstration of exactly how this process is supposed to work. Patient, self-correcting, willing to abandon an exciting story the moment better data demands it. But even as that specific thread cooled, it left behind sharper tools and a community more attuned than ever to the places where the standard model's predictions and nature's actual behavior might still quietly diverge. And it is in one of those remaining cracks that the story gets stranger still. That crack involves the same muon, but a different kind of measurement entirely, one that has nothing to do with how it decays and everything to do with how it wobbles. To understand it, picture standing on the deck of a ship somewhere in the middle of a vast, windless ocean. The surface looks like flat glass stretching to the horizon, utterly still, seemingly empty. But you know intellectually that this calm surface is a kind of illusion because miles beneath it lies a pitch-black abyss, churning with crushing pressure, unseen currents, and enormous creatures moving silently through the dark. Hold on to that image because it turns out to be a surprisingly accurate description of empty space itself. For most of scientific history, a vacuum was assumed to be exactly what the word implies, nothing. Remove every particle of matter from a box, shield it from every stray photon, and you should be left with pure emptiness. But as physicists dug deeper into the quantum foundations of reality over the 20th century, they discovered something deeply unsettling. True emptiness simply does not exist. Strip away every scrap of ordinary matter and space itself is still seething. A churning quantum sea in which particles are constantly, violently tearing themselves briefly into existence and annihilating each other again in fractions of a second, too fleeting to ever observe directly. We call these fleeting apparitions virtual particles, and they raise an obvious and uncomfortable question. How can something that barely exists, something that vanishes almost the instant it appears, have any measurable effect on the solid, tangible world around us? The muon gives us a direct way to test this. Like the electron, a muon behaves like a tiny spinning magnet, and when you place a spinning magnet inside an external magnetic field, it wobbles, in much the same way a spinning top wobbles as it slows down. The standard model predicts the exact rate of that wobble with extraordinary precision, accurate to roughly a dozen decimal places, once you account for the influence of every known virtual particle constantly bumping and jostling it as it moves through that churning quantum sea. When physicists actually measured that wobble in extremely precise magnetic ring experiments, first at Brookhaven National Laboratory and later with even greater precision at Fermilab, the muon stubbornly refused to match the prediction. It wobbled just slightly faster than the equation said it should. That discrepancy sat right at the edge of statistical significance for years, tantalizing enough to keep theorists awake at night, yet never quite decisive enough to declare a genuine break from the standard model. Complicating matters further, some of the most sophisticated theoretical calculations of what the prediction should even have themselves shifted over time as computing power and technique have improved, narrowing the gap between prediction and measurement in ways that have made this one of the most contested and closely watched numbers in modern physics. Whether this particular wobble turns out to be a genuine crack in our understanding or an artifact of an incomplete calculation remains, as of now, a genuinely open question. One of the very few places in physics where careful people can look at the same numbers and reasonably disagree. But suppose, for the sake of exploring the idea fully, that some version of this anomaly holds up under future scrutiny. What would it actually mean? It would mean the muon, as it moves through space, is not simply drifting through a void. It is pushing through an active, invisible ocean of virtual particles, constantly buffeted by ghosts. The standard model already accounts for every known ghost, every virtual version of every particle we have already discovered, and folds their influence carefully into its predictions. If the muon's wobble genuinely refuses to match that accounting, even after every correction is applied, it suggests the muon may be colliding with phantoms that do not appear anywhere in our current blueprint of reality. Think about the weight of that possibility for a moment. The solid, tangible, measurable world you and I inhabit, would turn out to be shaped in some small but real way by an invisible shadow realm of particles that borrow energy from the universe and repay the debt before it can ever be collected. We would no longer simply be missing one piece of a puzzle. We would be forced to entertain the possibility that the puzzle itself is resting on a table we cannot see, built from materials our instruments were never designed to detect. Human intuition tends to fail us completely at this point, and it should, because the next idea asks you to abandon almost everything your senses have ever told you about the shape of space. Look around whatever room you happen to be sitting in. Walls, ceiling, floor, the comfortable geometry of up and down, left and right, forward and backward. We navigate this three-dimensional world so effortlessly that treating space as anything other than an empty, static stage feels almost unthinkable. Even when Albert Einstein revealed that space and time are woven together into a single flexible fabric that can stretch and warp to produce gravity, it was still in some sense a stage, one that bends and curves, but a stage nonetheless. What if some of the unresolved anomalies still being chased through particle data are not simply new characters walking across that stage, but subtle clues that the stage itself is incomplete? Consider a long, thin garden hose stretched across an open lawn. Viewed from 100 feet up, it looks like a simple one-dimensional line, and an ant crawling along it would appear to have only two choices, forward or backward. But walk down and look closely, and you notice the hose has thickness, a second dimension curling around its circumference that was completely invisible from a distance. The ant, it turns out, can also walk around the hose, tracing a tiny circular path invisible from far away. Certain branches of theoretical physics, most famously string theory, propose that the fabric of our universe might work in exactly this way. We experience the large, open dimensions of space every day, but at every microscopic point, there could be additional dimensions, perhaps 6 or 7 of them, curled up into geometric shapes so unfathomably small that no particle accelerator built so far has been able to see them directly. This idea offers a strange but genuinely elegant explanation for one of the deepest unsolved puzzles in physics: why gravity is so bizarrely, almost embarrassingly weak. A small refrigerator magnet can lift a paperclip clean off a table, effortlessly overpowering the combined gravitational pull of the entire planet beneath it. By any reasonable intuition, gravity should be a titan among forces, yet it is by far the feeblest of the four. One proposed explanation is that gravity is not actually weak at all within its own dimension. It simply leaks. If gravity, unlike the other forces, is able to spread out into those hidden, curled-up dimensions, rather than staying confined to our familiar three, its strength within our slice of reality would appear diluted, stretched thin across geometry we cannot perceive. If certain undiscovered particles were similarly able to slip briefly into those hidden dimensions and back again, they would look to us exactly like fleeting ghosts, nudging a muon's wobble or tugging slightly at a quark's decay before disappearing back into a geometry our detectors were never built to see. This remains firmly in the realm of hypothesis rather than confirmed fact, but it illustrates just how far theoretical physicists have been willing to reach in trying to explain even small, contested discrepancies in the data, and how much genuinely strange territory sits just beyond the edge of what we currently know for certain. It is worth pausing here to be honest about something important. Speculative, as these extra-dimensional ideas are, they represent one end of a much broader, more grounded scientific effort. Most of the work happening at the Large Hadron Collider today is not chasing dramatic fifth forces or hidden dimensions. It is the painstaking, unglamorous business of measuring known particles with ever greater precision, or closing tiny gaps in our understanding, and occasionally ruling out entire families of exotic theories that failed to show up where predicted. That is not a lesser kind of science. It is, in many ways, the whole point. Every genuinely revolutionary shift in physics, from Newton's gravity to Einstein's relativity to the birth of quantum mechanics, began with exactly this kind of patient, careful measurement, decades of unglamorous data collection punctuated by the occasional small discrepancy that refused to resolve itself, and eventually forced a complete rethinking of the rules. Consider how thoroughly our intuitions have already been rebuilt once before. For nearly 2 centuries after Isaac Newton described gravity with mathematical precision, we lived inside a comfortable, clockwork universe, predictable, mechanical, reassuring in its rigidity. Then, Einstein came along and shattered that clockwork, revealing a universe built from a bendable fabric of space and time. Not long after, the pioneers of quantum mechanics shattered that smooth fabric all over again, revealing a chaotic underlying realm of probability and uncertainty at the smallest scales. Each time physicists believed they had found the final answer, nature gently but firmly reminded them they had only glimpsed a shadow on the wall of a much larger cave. There is no particular reason to assume that process is finished. Whatever unresolved anomalies survive the coming decade of more precise measurements, whether they point toward new particles, new forces, hidden dimensions, or simply a deeper and more complete version of the standard model we already have, the pattern is likely to repeat itself in some form. The universe has never been under any obligation to make intuitive sense to a species of primates whose brains evolved to track predators across a savanna, not to visualize 11-dimensional geometry. That mismatch between our evolved intuition and the actual texture of reality might be the single hardest truth in all of this. Evolution spent millions of years wiring your brain to trust that a rock is solid, that water flows downhill, and that the ground beneath your feet will hold your weight because those instincts kept your ancestors alive. None of that required any understanding of quantum fields or curled-up dimensions, and so none of it prepared you or any of us to intuitively grasp what physicists now believe may lie beneath the surface of ordinary matter. At the deepest level physics can currently describe, the picture is not one of tiny solid billiard balls waiting patiently to be discovered inside smaller and smaller boxes. It is a picture of vibration, of invisible fields stretched across the whole of space, plucking out something closer to musical notes than solid objects. Under this description, you are not built from little pieces of stuff so much as you are a remarkably stable, remarkably complex pattern of interacting quantum fields, a kind of standing wave that has persisted long enough to read these words. That is a genuinely strange thing to sit with, and it is part of why so many physicists find the deepest layers of their own field almost impossible to visualize, no matter how comfortable they are with the underlying mathematics. None of this means the door has swung open and the answer has already walked through it. Most of the specific anomalies that once electrified headlines, the beauty, quark, decay imbalance chief among them, have either faded under closer scrutiny or remain genuinely unresolved rather than confirmed. That is simply how frontier science works. The vast majority of promising cracks in an established theory turn out, on closer inspection, to be flaws in measurement rather than flaws in the model. And the ones that do survive scrutiny tend to survive by a razor-thin margin for years before anyone is willing to call them a real discovery. What makes this moment genuinely interesting is not that physicists have found definitive proof of a fifth force or a hidden dimension. It is that, for the first time in decades, there are multiple independent threads, precision measurements of the muon, deeper theoretical questions about gravity's weakness, and a broader unease about the gaps the standard model was never built to fill, that are all quietly pointing in directions our current blueprint cannot fully explain. Whether those threads eventually weave together into a genuine new discovery, or dissolve one by one under the weight of better data and better calculations, is precisely the question the next decade of experiments is designed to answer. And it is a question nobody currently knows the answer to, which is exactly what makes it worth paying attention to. It helps, too, to remember just how enormous the machinery behind all of this actually is, because the scale of the effort says something about how seriously the physics community takes even the smallest discrepancy. Thousands of scientists from dozens of countries collaborate on detectors the size of apartment buildings, built with the precision of a fine watch and the ambition of a cathedral, all in service of catching a handful of anomalous events buried inside quadrillions of ordinary, boring collisions that behave exactly as expected. Most of what happens inside that 17-mile ring on any given day confirms the standard model rather than challenges it, which is itself an important part of the story. A theory does not earn the title of most successful in the history of science by being wrong most of the time. It earns that title by correctly predicting the outcome of experiment after experiment, decade after decade, with a level of precision that borders on the uncanny. The anomalies we've been discussing are interesting precisely because they are rare, precisely because they stand out against a backdrop of overwhelming agreement between prediction and observation. That contrast is what gives a stray data point its power. If everything in physics were already in constant disagreement with theory, nobody would think twice about one more inconsistency. It is the fact that the standard model gets almost everything right that makes the handful of places where it might be getting something wrong so significant. There is also something worth appreciating in how slowly and carefully this kind of discovery, if it ever fully arrives, is allowed to unfold. Unlike so much of modern life, where information moves at the speed of a headline and conclusions are expected within the hour, the search for a crack in the foundations of physics moves at the pace of exhaustive verification. Every anomaly is checked, rechecked, torn apart by skeptical colleagues looking for any possible flaw, and then checked again with fresh data before anyone dares use the word discovery. That patience is not a weakness of the field. It is the entire reason we can trust the standard model as deeply as we do in the first place. The same rigor that eventually dissolved the beauty quark anomaly back into ordinary agreement with theory is the very same rigor that would one day confirm a genuine break from it, if one is truly there to be found. Science does not reward the anomaly that merely looks exciting. It rewards only the anomaly strong enough to survive years of people actively trying to make it disappear. So here is where that leaves us. Beneath the French and Swiss countryside, an extraordinary machine continues to smash matter together at nearly the speed of light. And the mountains of data it produces are still being combed through, refined, and argued over by thousands of scientists who genuinely do not know yet whether they are chasing ghosts or standing at the edge of the next great rewriting of physics. We have taken apart the antique pocket watch of the standard model piece by piece, found its long-missing gear in the Higgs Boson, and then discovered almost immediately afterward that the watch might only be the outer casing of something far larger and stranger underneath. We have peered into the churning quantum vacuum and found it anything but empty. We have entertained the possibility that the space around you right now might be hiding extra dimensions folded up smaller than any instrument can currently resolve. And we have had to confront the deeply humbling possibility that the ultimate architecture of reality may simply be too abstract, too mathematical to ever be fully pictured by a brain built for tracking footprints and firelight. Some of the specific cracks we started with have already closed back up under more careful measurement, and that is not a failure. It is science functioning exactly as it should. Others remain stubbornly, tantalizingly open. Whichever way those remaining threads resolve, the deeper question underneath all of it is not going anywhere. When the dust from this new round of measurement and argument finally settles, and physicists either confirm a genuine crack in the standard model or fold these last anomalies quietly back into the theory we already have, what will that mean for the story we tell about what the universe and everything inside it actually is?